Now we learn about causes of lanthanide contraction. We know that lanthanide series, then lanthanide contraction causes are given. We know that as we proceed from one element to the next one in lanthanide series, the nuclear charge means atomic number increases by +1 at each next element. Thus, as we move from cerium to lutetium, the attraction between the nucleus and the outermost shell electron increases gradually at each step. It is also known that as we move from cerium to lutetium, the addition of extra electron takes place to 4f orbital. Since 4f orbital have very diffuse shape, the electrons in these orbitals are not able to shield effectively. The attraction of the nucleus for the electrons in the outermost shell as the atomic number of lanthanide increases. Thus, it is only due to the gradual increase in the nuclear charge, that is, increase in the attraction between the nucleus and the outermost shell electrons, that the size of lanthanide atoms and M3 plus ions decreases gradually with atomic number. The above discussion shows that it is due to the poor shielding effect of 4f electrons and gradual increases in the nuclear charge that the lanthanide contraction takes place among lanthanide. Then, consequence of lanthanide contraction. Lanthanide contraction plays an important role in the determining the chemistry of lanthanides and Heaver transition series elements. Some important consequences of lanthanide contraction are discussed below. First point is basic character of lanthanide hydroxide, means MOH3. Due to lanthanide contraction, the size of lanthanide means +3 lanthanide ions, that means M3 plus ions, decreases regularly with increasing atomic number. As a result of this decrease in size, the covalent character between M3 plus ion and OH minus ions increases from lanthanum to lutetium. Therefore, the basic character of the hydroxides decreases with increasing atomic number. Consequently, lanthanum hydroxide is the most basic while lutetium hydroxide is the least basic. Means lanthanum hydroxide is more basic than the lutetium. Similarities among lanthanides: because of very small changes in the radii of lanthanide, their chemical properties are quite similar. It is due to their similar properties that the lanthanides cannot be separated from each other in pure state. Recently, methods based on repeated fractional crystallization or ion exchange technique, which take the advantage of slight difference in their properties like solubility, complex ion formation, hydration, etc., arising from very slight size differences of their trivalent ions have been used. Next is lanthanides possesses high density. Density is equal to atomic weight upon atomic value. Due to small atomic size, the packing of atoms in their metallic crystals becomes so much compact that their densities are much high. The densities of the elements of the third transition series are almost double than densities of the elements of second transition series. Next is the lanthanide show chemical twins. In first topic we see due to similar properties that lanthanides cannot be separated. And here we see the lanthanides show chemical twins. The elements following the lanthanides, that is post lanthanide element, hafnium, tantalum, tungsten, do not show the expected increases as atomic volume. Hence, they show extraordinary similarities with their preceding members of the group: zirconium, niobium, and molybdenum. From titanium to zirconium, atomic volume increases, and in hafnium, atomic volume is expected to increase than that of zirconium. But due to lanthanide contraction, the atomic volume is nearly equal to that of zirconium. Hence, zirconium, hafnium show extraordinary similarities. Hence, the chemical separation of zirconium and hafnium is carried out with difficulties. Similarly, due to lanthanide contraction, the pairs of niobium, titanium, molybdenum, tungsten, these show extraordinary similarities. These pairs are called chemical twins. In following table, we show some ionic radii of transition metals. Thank you.